As promised, there is a second video for 6-1 since we are still in quarantine, and for future generations, if you're watching this video, you probably know what this is about. Okay, so the one thing that I didn't do for chapter 6, section 1 in my previous video is actually talk about the word problems, and this is where it gets interesting. These are just equations, but they model very specific things, very applicable to your life. Exponential growth and decay can describe anything from population growth to the devaluation of a car. Also, this is where we can start learning about saving money in savings account with compound interest. So we are going to have to be together on page 298. We're going to have to look at the examples to answer the questions at the bottom of the page, because that's how this book works. So I'll do my best to focus the camera, but you should be on page 298 with me. I'm going to go fast to get an idea for example 2, and then we're going to skip down to the bottom and do monitoring progress number 5. And then we'll do something similar for example 3. And by the way, something similar for example 5. All right, so 6-1, word problems and compound interest is where we're at. Okay, solving a real life problem. And this is a real life problem, finally, not talking about a rocket going up into space and then coming down in the beginning of the year like we probably did with parabolas. The value of a car, Y, in thousands of dollars, can be approximated by the model this, where T is the number of years since the car was new. All right, first of all, I'm just kind of getting an idea of what's here. You should do the same. I'll go back and fill in the math later. All right, tell whether the model represents exponential growth or exponential decay. Okay, so now I can go back. Here's the equation. The base is 0.85 and it's less than 1. So it's going to be decay. All right, oh, there's an answer. Identify the annual percent increase or decrease in the value of the car. Ooh, all right. Annual percent increase or decrease. Increase or decrease from what? Increase or decrease from 1. 1 is 100%, right? 1.00 as a percent is 100%. So if it didn't increase or decrease in value, it would be times 1, times 1, times 1, times 1, times 1. But it's not. The base is 0.85, which means that it's 1 minus 0.85, which gets you 0.15, or a 15% decrease. And then this is a different way of looking at it, by the way, the book says it. So 0.85 is 1 minus 0.15. So in other words, 85% is how much off of 100%? It's 15% off. We know it's decay. It's a 15% decrease. And then, okay, estimate when the value of the car will be $8,000. In a normal world, we have graphing calculators, and I show you how to do this with the table. I'm actually going to show you on Desmos with the graph, and it's about the same exact thing. Actually, here they do that with the trace feature, and then later on they tell you how to use the table feature. So I'm going to use the trace feature on Desmos. All right, but this is already done for us. So let's go down to number 5 and make sure that I'm not giving anything away. In example 2, all right, in example 2, the value of the car can be approximated by the model, this equation. Identify the annual percent decrease in the value of the car. Estimate when the value of the car will be $8,000. Okay, so if you need to pause and copy this down, you should, but obviously your book should be open in front of you because it's not just about the screen. However, here we are. And just a reminder, page 298, number 5. Okay, so we were talking about example 2, and we kind of had to know, we really did have to know what example 2 is about. Okay, here's the equation. Identify the annual percent decrease. I love my shorthand. All right, well, here's our base. It's 0.9, definitely decay. It's less than 1. And, well, 0.9 is how much away from 1.0? 0.1, or 10%, right? Move it to the right twice. So again, 0.9 plus 0.1 gets you 1, or how far away is 0.9 from 1, or what is 1 minus 0.9? there's many different ways of looking at it. Okay, and now we have to estimate when will the value of the car be $8,000. Now, I actually want to show you something that the book does not show you yet. Let's remember that Y is your value of the car. So we are actually trying to solve this equation, okay? The book doesn't get here yet. We're going to get to it soon. We're trying to solve this equation. Now, all right, here is the problem. The variable is up here, and we have not learned that yet. So we could do some math to get ourselves set up, right? But right now, we're going to go to Desmos. We're going to graph it, and I'm going to show you what to do. So make sure you're taking notes. Okay. All right, so let's just type it in. We got to make sure we type it in correctly. You know I'm a fan of parentheses when they have them here, so we're going to use them. And we could use T. It doesn't really matter. I have to zoom out. Here we go. Okay, so it's definitely decay because it's starting up here and it's going down here. So we want to know when. All right, so that's our time. When will the function be $8,000? When, sorry, yeah, how long will it be for the car to get to $8,000? Sorry, I keep repeating myself because I'm realizing that I skipped over a very important thing, and it says in the book that Y is in thousands of dollars. So I actually shouldn't have put 8,000 into the equation. I should have put 8. Let me show you real quick, just so we are clear. So it wasn't 8,000. Y is supposed to be in thousands of dollars, so it's 8. And we do 8 divided by 25. We could do math. We're not doing the math. We're using Desmos. But what are we using Desmos to find? When Y is equal to 8. So you're just going to take your cursor. I was wondering why this looked weird. I'm going to zoom in so that we can definitely see. All right, 5, 6, 7, 8. Excuse me. 5, 6, 7, 8. And so I'm going to just hold my mouse down and try to find as close as possible to 8 on the in the Y value. And that's about 10.8 years. The X value is 10.8. So the answer will be 10.8 years. It's a little clunky because it's estimating. And I'm not used to doing that, by the way. So when will it be $8,000? The key was, what I forgot is that you plug in 8, which means we're looking for 8 on the Y-axis, and that gives us a T of approximately 10.8 years. All right, we're going to do something similar again with number 6. But to do number 6, we need to read example 3. In 2000, the world population was about 6.09 billion. This is true, by the way. During the next 13 years, the world population increased by about 1.18% each year. This is true, by the way. Write an exponential growth model giving the population Y in billions, so 6.09 instead of all the zeros, T years after 2000. So after 2000 means that T is equal to 1 means 2001. T is equal to 10 means 2010. And then estimate the world population in 2005. All right, so let's take a look at what they did down here. The initial amount, A, is 6.09. All right, well, that's great. So we plug 6.09 into A for this here. By the way, you get this equation from the previous page. So stop and turn back. And the percent increase is 0.0118. Right? Because 1.18%, we have to move it 2 times to the left to get us the decimal value. So the growth model is going to be 6.09 in front. We know it's growth, so 1 plus 0.0118 to the T power. All right. Now, so they set this up in all these words. We're going to do one together, don't worry. And then they say, all right, find out when, estimate the world population in 2005. Well, T is years after 2000. So they plugged in 5. They used their calculator or Desmos, and they got 6.46. And then they added the word billion to the end of it. I apologize that my phone keeps going off. Okay. Then estimate the year when the world population was 7 billion. We'll get to that. They showed you how to do it in a table. We're not using a graphing calculator together as a class in the year 2021, but in 2022, hopefully we will be if I'm using the same video. Anyway, I'm going to show you how to do it on Desmos, but basically when the world population 7 billion, so 7 is your Y, we're looking for 7 on the Y axis and finding out the T or the X, and that's going to be the years after 2000. Okay, deep breath with me. We have to now do, in example 3, this is number 6 at the bottom page, assume the world population increased by 1.5% each year instead of 1.18%. Write an equation to model the situation, estimate the year when the world population was 7 billion. All right, something similar. All right, we need to write an equation though, and I did skip over the fact that the equations for growth and decay are at the bottom of page 279 because they're actually kind of simple. So we know this is growth, it has a plus sign. If it was decay, it has a minus sign. Now the rate has to be a decimal. So it can't be 1.5%, it has to be 0.015. I try not to write the 0 in front, just it gets me confused. If it doesn't get you confused, go ahead and write it. So y equals, now A is your initial amount, So what was the initial amount in the year 2000? Since this is all models after the year 2000, it was that. And we're going to do 1 plus 0.015 to the T, and let's make it pretty. Okay, so here is our equation. Let's go read this. Write an equation to model the situation. All right, here it is. Estimate the year, so that's T. So we're looking for T when the world population was 7 billion based on this model. Now let's remember the Y stands for the population in billions. So when will it be 7? Again, the book's not doing this yet, but I want to because I want you to see where we're going. And we're solving for T, which is the problem. It's in the exponent. And we have to remember that's the years after 2000. So let's go to Desmos and we're going to plug this in right here. Y equals 6.09 times 1.015 to the T. Ooh, wow, it's really flat. I wonder why. Does it have anything to do with the fact that it's really close to 1? Yes, it does. That's literally why. Okay, we want to know when the world population, the Y, is going to be 7, and we're estimating. So we just need to hold down and get as close as possible. And honestly, I'm not rounding to the hundreds. I'm going to round to the nearest whole year. So I'm going to say it's around, or not around, oh, we could just say in the year. It's in the year 2009. It looks like it's the year 2009 and 4/10, whatever that month is, not necessarily April. So 9 on the T or the X means that it's 2009. So T is 2009, and that's according to this model when the world population gets to 7 billion.